Hello and welcome back to the Deep Dive. Today, you and I are embarking on an intellectual adventure that might sound, well, a little formidable at first, pure mathematics. But I promise you, it's packed with incredible insights, moments of true genius, and even a good dash of historical intrigue.
Absolutely. It's a fascinating area.
We're going to plunge into the heart of a truly foundational text. Harold M. Edwards's Riemann's zeta function, published by Academic Press way back in 1974. Now, this isn't just another math book. It's considered an absolute classic for some very compelling reasons we're about to unpack.
It really is a landmark publication in the field.
Our mission on this deep dive is, well, threefold. First, we'll thoroughly explore the profound contents of Edwards's monumental work, understanding its structure and the clarity it brought to a complex subject. Second, we'll appreciate its monumental contribution, seeing how it meticulously traces the lineage of Riemann's ideas. And finally, with the benefit of, wow, 5 decades of hindsight, we'll consider what groundbreaking new discoveries have emerged since its publication, what it inevitably couldn't have covered, and how these later developments stand on the shoulders of works like Edwards.
That's a great way to frame it, looking back with today's knowledge.
Yeah, think of it like this. We're peering through a powerful telescope built in the 1970s, getting an astonishing view of the universe of the Riemann zeta function, and then we'll discuss what modern instruments, like Hubble and James Webb, have shown us in the decades since. Okay, let's unpack this.
It's particularly striking how Edwards' book isn't merely a textbook just listing results. It's really a masterclass in mathematical exposition, designed to truly illuminate a complex subject right from its deepest roots.
That's the key word, isn't it?
Exactly. And the fact that it won the Leroy P. Steele Prize for Mathematical Exposition from the American Mathematical Society in 1980, well, that speaks volumes about its unparalleled clarity and profound impact. It has this remarkable ability to take what is inherently dense and make it genuinely accessible, acting as a crucial bridge between Riemann's original, often quite cryptic, insights and, well, contemporary understanding.
And that Steele Prize isn't just, a pat on the back. It highlights Edwards' remarkable skill in translating such complex material into something genuinely comprehensible. That's a rare talent in mathematics, as you said.
Very rare indeed. So let's begin by grounding ourselves in the context of this remarkable book. Who was Harold M. Edwards? He was a noted mathematician and educator, primarily based at New York University, celebrated for a teaching philosophy that prioritized understanding and accessibility over, say, rote memorization.
Right, making it understandable was his focus.
Right.
Exactly. And this book is a prime example of his dedication to making profound mathematical ideas transparent. Published in 1974, it was part of a highly prestigious series called Pure and Applied Mathematics, edited by intellectual giants like Samuel Eilenberg and Hyman Mars from Columbia University.
Wow, Eilenberg and Bars. That tells you something.
It immediately signals the rigorous academic weight and uncompromising standards behind this work. The publisher's stated goal for the book was to deeply examine and amplify Riemann's original 1859 paper, then meticulously trace the subsequent theoretical developments it inspired. It's essentially a scholarly journey that begins precisely at the source, offering you a comprehensive historical and mathematical lineage.
This brings up a really important question. Why is an expository book considered so valuable, maybe even indispensable, in a field like advanced mathematics?
Good question. What's your take?
Well, it's because it moves beyond just presenting theorems and proofs. An expository work, particularly one as acclaimed as Edwards, delves into the why and how. It guides the reader through the intricate thought processes, the historical context, the intellectual struggles that led to these groundbreaking discoveries. Edwards didn't just summarize Riemann, he provided a meticulously paved pathway to understanding Riemann's revolutionary, yet often incredibly dense, ideas.
Oh, it's about the journey, not just the destination.
Precisely. And to truly grasp its standing, consider the company this book kept. The Pure and Applied Mathematics series was, a hub for highly specialized, cutting-edge mathematical texts. Some of its other titles, for instance, included things like Homology Theory, An Introduction to Algebraic Topology.
Right, counting holes in spaces, basically.
Sort of, yeah. Or Differential Algebra and Algebraic Groups, which merges abstract algebra with differential equations. These are not, light popular science reads. They represent the absolute forefront of mathematical research and exposition, from theoretical physics to pure number theory. Edwards' inclusion in this collection thus unequivocally solidifies the profound academic caliber and intellectual significance of his contribution.
That context really hammers home the caliber of the work. It reinforces that this isn't just a survey, but a deep, deep engagement with the material. Now, at the very heart of Edwards' book, and where he truly shines, is his almost surgical illumination of Ryman's original paper itself.
Absolutely. Chapter 1.
He dedicates its entire first chapter to Ryman's paper, even including a full translation of it in the appendix. Which is incredibly valuable because, as you can imagine, Ryman's original 1859 paper on the number of primes less than a given magnitude, it's foundational, but it's famously terse, difficult to penetrate, and not always easy to access directly, especially in the original German.
Terse is putting it mildly sometimes.
Right. Edwards breaks it down with meticulous care, starting with the historical context. He paints a vivid picture of the mathematical landscape Riemann was operating within, what questions were on mathematicians' minds, the tools available.
Setting the stage properly.
Exactly. Then he dives into the Euler product formula. This isn't just some algebraic identity, it's a profound conceptual bridge. It reveals how the seemingly continuous world of analysis through the zeta function is intrinsically tied to the discrete, irregular world of prime numbers.
That connection is just mind-blowing when you first grasp it.
It is. Edwards shows how Euler's stroke of genius allowed mathematicians to start studying prime distribution using powerful analytical tools, laying the entire foundation for Riemann's later, even more audacious conjectures. It fundamentally shifted how we viewed primes, from isolated curiosities to components of a grand underlying mathematical harmony.
A fundamental shift, definitely.
He also covers the functional equation. And this isn't just a formula, it's a revelation of a deep, almost mystical symmetry property of the zeta function itself.
The symmetry is key.
It effectively states that the function's behavior on one side of a particular line, the critical line, mirrors its behavior on the other. This isn't just mathematical elegance, it's hugely practical. It drastically reduces the area mathematicians need to search for the zeta function's non-trivial zeros.
Cuts the work in half, essentially.
Pretty much. If you find one, a corresponding zero exists. Edwards helps us appreciate how this inherent balance is a cornerstone of understanding the function's global structure. And crucially, he tackles the roots of these mysterious zeros of the function, especially those in the critical strip. The book then illuminates the profound connection between S and primes, showing how the distribution of these roots directly influences the distribution of prime numbers. That's the heart of it, really.
That's the magic, yeah, the link between zeros and primes.
Finally, Edwards explains Riemann's main formula and the formula for Jx, his explicit formula for the prime counting function. Just a breathtaking achievement. It's remarkable how much Edwards makes sense of. What for you is the most striking aspect of Edwards' decision to anchor the book so deeply in Riemann's original contribution?
Well, it's precisely that anchoring in Riemann's original thought that is Edwards' genius, I think. If we connect this to the bigger picture, by analyzing Riemann's paper in such depth, Edwards doesn't just explain what Riemann did, but also why it was so profoundly significant, how he arrived at these conclusions, the intellectual leaps he made.
Right, the process.
Exactly. He unpacks complex concepts like Riemann's ingenious use of the Fourier inversion method. Essentially, this technique lets you transform information from one domain, like the frequency domain, to another, like the time domain. Riemann brilliantly applied it to translate the abstract positions of the zeta function's zeros in the complex plane into concrete, explicit formulas for counting prime numbers like Jx and Uxx.
So transforming abstract locations into actual counts.
That's the idea. It's like using the harmonics of a sound to reveal the shape of the instrument producing it. The lyros are the harmonics. And Fourier inversion allows us to hear the distribution of primes. The brilliance here is that Edwards doesn't just present these ideas. He makes you, the reader, understand the intellectual journey Riemann undertook.
That's fantastic.
And crucially, Chapter 1 also addresses questions unresolved by Riemann. This is a masterstroke in an expository work because it explicitly lays out the challenges and mysteries that Riemann himself couldn't fully solve.
Setting the stage for what's next.
Precisely. It sets the stage for future mathematical endeavors and indeed for the rest of Edwards' book. It shows where the field stood and where it still needed to go, highlighting the tantalizing questions that would drive decades of research. It's a testament to Edwards' insight into the mathematical process itself, not just the results.
That's an incredibly crucial point. It reminds me how much mathematical progress often stems from these open questions, these explicit challenges that Edwards laid out, almost like a roadmap for future generations. Now, Edwards doesn't stop at merely deconstructing Riemann's original paper.
No, he keeps going.
He then meticulously traces the theories and methods inspired by it, carefully following the threads of inquiry right up to his publication date. It's like a guided tour through the evolving mathematical landscape of the zeta function, seeing how an initial spark ignites, well, a whole forest fire of research.
A very apt analogy.
After establishing Riemann's foundational work, Edwards doesn't just jump to the next big thing. He meticulously guides us into how mathematicians began to build upon Riemann's insights to rigorously prove the very structure of the zeta function. This is where Chapter 2, the product formula for Char, takes center stage.
Right, the infinite product representation.
Exactly. It's not merely about deriving a formula. It's about revealing the intrinsic architecture of the function, showing how its elegant product representation emerges from the careful study of its roots. He delves into tools like Jensen's theorem.
Which helps count the zeros in a region.
Right, and how these detailed estimates ultimately lead to that elegant canonical product representation. What's particularly compelling about Chapter 2 is how it reveals the deep connection between the zeros of the function and its global behavior, essentially describing the zeta function by its building blocks, the zeros.
It shows how the zeros dictate the function's form.
Building on this, Chapter 3 is all about Riemann's main formula, discussing von Mangelt's formula for Jex and its proof. Here, Edwards shows how this formula significantly refines Riemann's original, maybe more approximate insights into prime distribution, providing a more precise and rigorous explicit formula for the prime counting function.
Moving towards greater precision.
It's a crucial step in translating the abstract properties of the zeta function into concrete information about primes. And then, in Chapter 4, Edwards brings us to what many consider a cornerstone of analytic number theory. The prime number theorem.
Ah, the PNT.
A huge result. Huge. This wasn't merely an improvement. It was a foundational answer to how primes are distributed, finally stating that primes are distributed roughly as x divided by the natural logarithm of x, SLN(x). This is a result you, our listener, are probably familiar with.
Probably heard of it, yeah.
And Edwards' genius lies in how he meticulously connects this elegant approximation back to the critical insights from Riemann's zeros. He unravels the intellectual journey of mathematicians like Hadamard and de la Vallée-Poussin.
Working independently.
Yes, showing how they're independent proofs by rigorously demonstrating that the real part of all non-trivial zeros, r is strictly less than 1, provided the ultimate rigorous foundation for this crucial understanding of prime distribution. It's less about what the PNT is and more about how it was proven through the lens of the zeta function.
The proof strategy is key.
And the subtle interplay between analysis and number theory that Edwards illuminates. This was a monumental achievement, moving from hypothesis to proven fact directly through understanding the zeta function's behavior.
A true landmark in mathematical history.
Finally, in Chapter 5, we get to de la Vallée-Poussin's theorem, discussing his improvements on error estimates. While Hadamard and de la Vallée-Poussin proved the PNT, the precision of that prime distribution, the error term, that's where the Riemann hypothesis truly lives.
Right, the accuracy of the approximation.
Edwards shows how de la Vallée-Poussin pushed these boundaries, laying the groundwork for the ongoing quest for tighter bounds on those errors, an area inextricably linked to the truth of the Riemann hypothesis itself.
What really stands out here is how Edwards orchestrates these chapters. He shows the organic evolution of ideas and, the deeply collaborative nature of mathematical discovery, even when people work independently. The proof of the prime number theorem, for instance, was a monumental achievement of the late 19th century.
Culmination of decades of work.
Exactly. It represented the culmination of decades of effort to quantify the seemingly random distribution of primes. Edwards guides us through Hadamard's proof that rho for all non-trivial zeros, a critical conceptual and analytical step, almost simultaneously achieved by de la Vallée-Poussin.
Incredible timing.
He really was. And Edwards also details de la Vallée-Poussin's work, which not only provided an independent proof of the PNT, but also significantly improved upon the error spell of him. Estimate's a key area, as you said, that ties directly into the precision needed for the Riemann hypothesis. Edwards' narrative carefully illustrates how each successive development refined our understanding and brought us closer to the deepest mysteries of prime numbers, ultimately building this robust analytical framework around Riemann's initial conjectures.
It's clear that Edwards is guiding us through a mathematical epic, but beyond the theoretical proofs, mathematics isn't just abstract ideas. It's also about computation, about the messy but essential work of turning theory into numbers.
Absolutely. Getting your hands dirty with calculations.
Edwards dedicates significant portions of the book to methods for actually calculating the zeta function and, most importantly, locating its zeros. This is where abstract theory meets concrete numbers. This is where the rubber meets the road.
Couldn't have said it better.
Chapter 6, for instance, delves into the numerical analysis of the roots by Euler-Maclaurin summation. Far from being just a dry numerical method, Edwards reveals how this powerful tool becomes a critical magnifying glass. It lets mathematicians approximate sums and integrals with incredible precision to actually find and count those elusive zeta zeros in a given range.
Turning infinite sums into something manageable.
Precisely. He discusses the intricacies of Stirling series for approximating factorials and various techniques for computing the number of roots within a specific region. It's the moment abstract theory gets grounded in verifiable numbers.
Making it concrete.
Building on these foundational computational tools, Edwards introduces a truly ingenious method in Chapter 7, the Riemann-Siegel formula.
Ah, yes, the workhorse.
The workhorse, exactly. This isn't just any calculation method. It's a highly optimized asymptotic expansion, specifically crafted to evaluate the zeta function with incredible precision on the critical line, RELIS S12.
What? Right where the action is supposed to be.
Its power lies in transforming an infinitely long sum into a finite sum, plus a small calculable error term. Edwards meticulously breaks down its derivation, showing how this clever mathematical trick dramatically reduces the computational effort. It made the exploration of billions of zeros on the critical line feasible even with early computing power. It's the turbocharger for zeta function computation.
A computational game changer for sure.
And in Chapter 8, he takes us into the truly heroic efforts of large-scale computations. He discusses the work of early pioneers like Alan Turing.
Turing involved in this too.
Yes, his mechanical method, developed during World War II, was one of the first systematic approaches to search for zeta zeros. He also touches on Lamar's phenomenon, where some zeros were found to cluster unexpectedly, and the painstaking computations carried out by Rosser, Yohe, and Schoenfeld.
These were the supercomputers of their day.
Absolutely. Human minds and early electromechanical machines tirelessly searching for zeta zeros, pushing the boundaries of what could be verified numerically. It really makes you appreciate the dedication involved, often just to check whether the Riemann hypothesis held for the first few million zeros.
Incredible persistence. This naturally leads to an important question. Why were these computational efforts so critical? I mean, were they just checking?
Good point. What was the deeper significance?
Well, they weren't just for curiosity, I think. They provided crucial empirical evidence, right? They had to refine theoretical estimates, and they pushed the boundaries of what was mathematically verifiable. The Riemann-Siegel formula, in particular, dramatically increased the number of zeros that could be checked for adherence to the Riemann hypothesis, offering strong numerical support for its validity, even without a formal proof.
So, building confidence in the hypothesis.
Exactly. What's more, Edwards even includes a section in Chapter 7, Speculations on the Genesis of the Riemann Hypothesis. Now, I haven't reread that specific section recently, but it likely delves into how these early computational insights and observations didn't just confirm existing theories, but maybe actively informed and shaped the theoretical conjectures surrounding the Riemann hypothesis.
Ah, so computation influencing theory.
It highlights that beautiful, iterative interplay between computation and theoretical speculation in mathematics. It's a reminder that even the most abstract ideas can be explored through empirical numerical means.
It truly is, and it makes you wonder, if they could do so much with slide rules and early machines, what breakthroughs might they have achieved with today's power? Or perhaps the RH is just that hard.
Perhaps. It certainly shows relentless curiosity.
It really does. Edwards takes us even deeper into the analytical properties of the zeta function next, which are absolutely crucial for understanding its behavior and its zeros.
Moving beyond just finding them.
Right. In Chapter 9, he explores the growth of zeta as EA and the location of its zeros. This chapter introduces powerful concepts like Lindelöf's estimates and hypothesis, which are still active areas of research, by the way, probing how rapidly the zeta function can grow as you move far up the complex plane.
How big does it get? That's vital.
Vital for understanding where zeros might, or crucially, might not be. The three circles theorem, a classic tool from complex analysis, helps bound the function's values, giving us clues about where zeros cannot exist. And the Bohr-Landau theorem provides profound statistical insights into the average distribution of the zeta function's values, hinting at deep regularity even in its seemingly chaotic behavior far from the origin.
So understanding its magnitude and average behavior high up.
Exactly. Then in Chapter 10, we see the elegance of Fourier analysis applied to this field. Edwards shows how a modern functional analytic way of looking at Fourier analysis is applied to prime number theory.
Bringing in another powerful toolkit.
He delves into discussions of invariant and self-adjoint operators, and critically, how the functional equation of the zeta function itself can be interpreted through Fourier transforms. What's fascinating here is that Fourier analysis, which breaks down complex signals into simpler waves, allows mathematicians to transform information from the continuous world of the zeta function to the discrete world of prime numbers.
Like finding hidden frequencies.
Kind of like finding the hidden musical notes within a complex orchestral piece, yeah. This really shows the power of connecting different mathematical fields, drawing insights from one area to illuminate another. It gives you a different, powerful lens through which to understand that crucial functional equation.
A beautiful connection.
And in Chapter 11, the focus returns sharply to zeros on the line. This chapter covers Hardy's theorem, which was a monumental proof showing that infinitely many zeros of the zeta function actually lie on the critical line, recess 12.
A huge step forward. Not just near the line, but on it.
Exactly. A huge step, moving beyond mere conjecture or computation for the first few zeros. Edwards then discusses lower bounds for the number of these zeros, demonstrating that there are at least kt zeros and even at least kt log t zeros within certain regions as t gets large.
Giving some quantitative measure of how many.
Right. This provides concrete evidence for the abundance of zeros on the critical line, further bolstering the Riemann hypothesis, even if it doesn't prove it entirely.
What truly stands out here is how Edwards masterfully integrates these disparate areas of mathematics, Fourier analysis, complex analysis, to shed multifaceted light on the zeta function. That chapter on Fourier analysis, for instance, illustrates such a powerful, elegant way to understand the functional equation and its deep relationship to number theory.
It really showcases his skill in synthesis.
It's a testament to Edwards' ability to synthesize diverse, high-level information and present it lucidly. He shows how seemingly separate mathematical tools can be brought to bear on one of the most profound and challenging problems in number theory. These chapters really equip you, the reader, with a sophisticated toolkit for analyzing the zeta function from multiple perspectives. You move beyond just finding the zeros to understanding their deeper analytical context, their growth, their fundamental properties.
Then Edwards even includes this fascinating miscellany chapter, Chapter 12, showcasing the remarkable ubiquity of the Riemann hypothesis and related concepts across mathematics.
Kind of like, and another thing.
Exactly. For instance, he explores its deep connection to Fourier series, which are sequences of irreducible fractions ordered by size. It's not immediately obvious how these seemingly simple number theory objects relate to the complex zeros of the zeta function.
Not obvious at all.
But Edwards reveals how the distribution of Fourier fractions is intrinsically linked to the error term in the prime number theorem, and thus, ultimately, to the Riemann hypothesis itself. It's an unexpected and beautiful link between very different areas of number theory.
Wow, that's a connection I wasn't aware of.
He also delves into Denjoy's probabilistic interpretation of the Riemann hypothesis, a truly mind-bending idea.
Probabilistic? How so?
Denjoy suggested that the RH might be understood not as a deterministic property, but as a highly probable outcome if the coefficients of certain related series were to behave like random variables.
Huh. Like it's almost certainly true, statistically speaking.
Kind of. It offers a completely different, almost philosophical lens through which to view one of mathematics' most stubborn problems, showcasing the breadth of approaches Edwards considered. The chapter even includes a discussion of Selberg's inequality and an elementary proof of the prime number theorem, different angles on related problems, highlighting how central the Riemann hypothesis is.
It touches so many areas.
It really does. Now, the book also discusses other zeta functions in Chapter 12.11 and Weil's theorem. Though a review we looked at notes, this is an area where the book omitted related research that was just beginning to blossom.
Which makes sense for 1974.
Exactly. And that gives us a perfect segue into looking at what came after 1974.
Right, the limitations imposed by time.
So as we've established, Edwards' book is lauded as an influential classic and an excellent companion to the subject. But every book, no matter how superb or comprehensive, is a snapshot in time, isn't it?
Absolutely, a product of its era.
Mathematics, like any science, is a living, breathing field that constantly evolves, expands, and generates new questions. So what does a deep dive into this 1974 text reveal about what was not yet known or what areas really blossomed after its publication? This is where we get to appreciate the relentless and frankly exhilarating progress of mathematical discovery.
It's important to clarify, though, that when we talk about what's missing from a book published 50 years ago, it's absolutely not a critique of Edwards' work.
Not at all. It's a measure of progress.
Exactly. It's a testament to the ongoing vitality of mathematical research, a celebration of how much the field has grown. Edwards documented the state of the art brilliantly for his time, providing an unparalleled exposition of Riemann's original ideas and their direct descendants up to the early 1970s. The omissions are simply a natural consequence of knowledge expanding beyond the horizon of its publication date. They represent new frontiers that were just beginning to be explored back then.
Well said. The external review we referenced highlights two key areas that Edwards' book, by its very nature, omits. The first is related research on other zeta functions with analogous properties to Riemann's function.
Right, the broader family of zeta functions.
While he does touch on other zeta functions briefly in that miscellany chapter, the reviewer suggests a much broader body of research was emerging that wasn't fully integrated into a work of that period. The second significant omission mentioned is more recent work on the large sieve and density estimates.
Ah, yes. Very powerful techniques.
These are incredibly powerful tools that have become absolutely central to analytic number theory in the decades following Edwards' publication, offering completely new ways to tackle old problems.
It's truly fascinating how the study of other zeta functions has just exploded since 1974. We're talking about more general constructions like Dirichlet L functions.
Which are key for primes in arithmetic progressions, right?
Exactly. Or even zeta functions for algebraic varieties and other complex geometric objects. These generalized zeta functions often share deep analogous properties with Riemann's original, and understanding them provides profound insights not just into number theory, but also into algebraic geometry and even theoretical physics. Edwards laid the groundwork for understanding the zeta function, but the field dramatically expanded to what some might call a zetaverse, if you will.
A zetaverse, I like that.
Where the principles discovered through Riemann's work found application in vastly different, yet structurally similar, mathematical domains.
And what about the large sieve and density estimates? How did they change things?
Well, regarding the large sieve and density estimates, these methods represent a powerful and distinct set of techniques that were largely developed in the mid to late 20th century. They provide highly effective ways to count mathematical objects, particularly primes in short intervals or arithmetic progressions.
Like a more sophisticated way of counting.
Exactly. Imagine trying to count specific types of fish in a vast, turbulent ocean. The large sieve gives you a sophisticated net, capable of catching those fish with far greater efficiency than traditional methods. They've been instrumental in making progress on difficult problems that were beyond the scope of classical methods, allowing mathematicians to make profound statements about the distribution of numbers.
So they open up new problems.
They opened up new problems and provide ways to get better results on old ones. These are sophisticated tools that significantly advance the field of analytic number theory, and naturally they wouldn't have been fully mature or integrated into a comprehensive overview published in 1974. They emerged as new frontiers of research, defining the next generation of problems and solutions.
This is where it gets truly captivating, showing just how quickly mathematics can advance, even for foundational questions. The review specifically notes that Chapter 11 on zeros on the line, which covers Hardy's theorem and lower bounds, was written before the Levinson 13 result.
Ah, Levinson. That timing is remarkable.
What exactly is this Levinson 13 result, and why is its timing, the very year Edwards' book was published, so incredibly significant?
This isn't just a minor update, is it?
No, not minor at all. This begs a critical question. The Riemann hypothesis, as you know, posits that all non-trivial zeros lie precisely on the critical line, raised 12. Hardy proved back in 1914 that infinitely many zeros do indeed lie on this line. Fantastic achievement, but it didn't give a sense of their proportion.
Right, infinite could still be vanishingly small proportion.
Precisely. Levinson, in 1974, the very year Edwards' book was published, in fact achieved a monumental breakthrough. He proved that at least 1/3 of the non-trivial zeros of the Riemann zeta function lie on the critical line.
1/3. That's a concrete fraction. A concrete, positive proportion. This was a profound result. It didn't prove the Riemann hypothesis itself, obviously, but it gave the strongest evidence yet for a significant proportion of zeros lying on that critical line, providing a concrete lower bound. So while Edwards brilliantly summarized the state of knowledge before this specific breakthrough, its immediate publication highlights how new insights can emerge right at the very moment a foundational text is released.
Wow. Talk about timing.
It forever altered the landscape described in the book and made Edwards Chapter 11 a historical marker of the state of mathematics right up until that point. It was a stunning achievement that immediately became a new benchmark in the field.
So what does this all mean for us, for you, the listener, and for the enduring legacy of Edwards' work? Edwards-Riemann's zeta function remains, I think we can agree, a truly remarkable achievement.
Absolutely. Still essential reading.
A crystal clear, deeply insightful, and comprehensive guide to Riemann's original ideas and their subsequent developments right up to the mid-1970s. It's a text that was welcomed by students and seasoned mathematicians alike, even influencing mathematically inclined general readers who sought to wrap their heads around these profound ideas. It gives you the full picture of the foundational work, the classical papers, and the direct lines of inquiry that stemmed from Riemann's genius.
What's truly illuminating here is that even with all the new research areas, the large sieve, density estimates, Levinson's monumental work, the whole Zetaverse expanding the field Edwards' book remains absolutely essential.
Why essential even with the later stuff?
Because it teaches you the language, the history, and the fundamental techniques of the subject. It equips you to understand those later developments with a firm grasp of the underlying principles. It really is an excellent companion to the classical papers, providing the bedrock knowledge that allows you to then engage with the more recent advanced breakthroughs to appreciate how they built on what came before. It's a foundational text that continues to serve as an indispensable gateway into this profound and endlessly fascinating area of mathematics.
Indeed. And perhaps the biggest takeaway from our deep dive today is this. A book, even an influential classic like Edwards, is a testament to the knowledge and the intellectual horizon of its time.
A snapshot.
A snapshot, exactly. It's a solid, invaluable foundation, but the House of Mathematics is always under construction, with new wings, floors, and even entire new architectural styles being added all the time. How might the landscape of the Riemann zeta function look another 50 years from now? And what new classic texts will guide future generations through its ever-expanding universe?
That's the exciting question, isn't it?
Something to mull over as you continue your own deep dives into knowledge. Thank you for joining us on this deep dive into Riemann's zeta function.